Today, I would like to talk about a recent work I have done with my supervisor, Daniele, on how to extracting dark energy behavior from quantum gravity series. And for the quantum gravity, I referred to the group field theory. I think that there's not much people are familiar with this theory, so I will first give a brief introduction to the group field theory and and how to extract cosmological information from it. A group field theory is a field theory defined over group manifolds. Its background independent means that there is no space-time in the underlying formulation. The space-time has to emerge from the more fundamental degree of freedom. In fact, the quantas in group field theory represents the building block of the space-time. When the dimension is 4, the building block is just 4 simplex. And the essential ingredient for the theory is the field operator. In our case, it can be decomposed onto orthonormal basis kappa. Here, these Cx and the Cx dagger are annihilation and creation operators of the building block of space-time. And since we don't have a space-time at the first place, there is no time to represent the evolution. So we have to introduce a stagger field phi as the relational time to count the evolution of other quantities. For the cosmological use, we also need the observable, the total volume operator, in our case defined in the second quantized form with the C dagger and the C. And the dynamics are encoded in the effective action at the mean field level, meaning that this effective action is the expectation value of this action operator inside the condensed states. And the homogeneous universe at a given time correspond to the state correspond to the so-called coherent peak state, which is peaked on a given relational time phi 0, with the eta here is a peaking function, specifies the peaking property. And the dynamics is encoded in this sigma tilde. It's called the condensate wave function. And since our universe is also isotropic at the large scale, so this sigma tilde can also be decomposed, leaving the dynamical information into this sigma j phi. This j labels different modes labels what we call the different modes. And with the proper choice of the interaction, the equations of motion of this wave function decouple. In fact, if we consider to decompose it into the modular part and a phase part, we'll see that the phase part can be integrated once to give the first constant of motion is q here, and the equation of motion of rho can be written in this form. Here is lambda and mu are coupling constants. The advantage of this mode decomposition is that the total volume can be written as the sum over different modes. Here, this V is the volume of the building blocks labeled by the mode J. since we know the equatorial motion of this rho, we can get the dynamics of this volume, of the total volume, which is the modified Friedman equation. It's quite complicated. We have a sum over modes, and it's also depend on the parameters of individual modes. Can't be written in a form that only involves the total volume. But there are some arguments suggest that at a large volume, only a single mode will dominate. So we can, for the moment, ignore the sum over modes and and for the moment, we also ignore the interactions. We will get the simplified form in this case. And at a large volume, these two equations both approaches to constants. If we introduce the Newton constant G through this Mj, we get exactly the Friedman equation with free massless scalar field in the reaction time, meaning that this prime here presents the derivative with respect to the scalar field phi. To express our quantum effects more explicitly, it would be better to introduce the effective equatorial state. It's defined through the Hubble parameter. The dot means the derivative with respect to cosmic time t, and after some calculation, we can get its reduced form. We know that when this equatorial state W equals to 1, we get a free massless scalar field in the universe. And if this W less than -1, we get a phantom-like dark energy. This may lead to the Big Rip singularity, where the scalar curvature diverges when the volume is large, means that in every point of the space-time, the scalar curvature is infinite, which is unacceptable. So our goal here is to recover the phantom-like behavior from GFT models without the need of phantom matter. In the particle physics sense, means we don't consider about the possible Lagrange for the phantom energy. And our result is that the effective equatorial state can be written in this form. Since this B here is the positive constant, it's less than the -1, so it's correspond to phantom-like behavior. And at the meantime, since it approaches to -1 fast enough, the Big Rip singularity can be avoided. We will see in follows. But previous to that, we first consider the free case, where things is a bit simpler. We will see that at the free case, we can get the early time acceleration. So at a small volume, the interaction can be ignored, and the equatorial motion can be solved easily. The important thing is that the minimum value of this module is positive, larger than 0. Since the total volume is the sum over different modes, so the total volume will never vanish in our case. So there is no big bound singularity, but a bounce. And near the bounce, the equatorial state is negative, leads to an accelerating expansion. But in our case, the expansion won't last long and ends quickly. In fact, the number of E-folds here can be is bounded by this equation with C1 and C2 is are constants related to E, M, and Q, the parameters in the model. The bound can go infinity in principle, but either requires all EJ vanishes or all QJ vanish. So in general, we can say that the number of evils is indeed bounded, and the accelerating phase is cannot last long. We can consider to see the modification to the single mode case. We can consider that two mode case as an example. We see that the equinal state in the two mode case, the blue line is less than one. One is its asymptotic value, and it will approaches to one finally from below. In contrary, in the single mode case, the asymptotic value is approached from above. And in the interacting case, the similar behavior will happen, where there the asymptotic value would be -1, and in two mode case, the W approaches to -1 from below is to a phantom-like behavior. So now let's include the interactions. For simplicity, we further consider the approximation where the volume is very large and the interaction dominates. So we can ignore the free parameters. The equation can be solved easily, with which each mode diverges at this Fedge infinity for each mode, where this Fedge infinity can be given by the parameters associated with its work. Since the rho J diverges at this value of real time, we see that for all modes, the mode with the smallest Fedge infinity dominates at a large volume. And substitute the solution into the definition of effective equinal state. We see that in our case, the equinal state depends only on the ratio rho 2 over rho 1. And take a further approximation. We set n equal to 6 and assume that phi 1 infinity is less than phi 2 infinity. At a large volume, rho 1 will dominate, and this R here approaches to 0. We can approximate this W further to give the result we promised, with this B is a positive constant. So here is the behavior of the equinal state in the two mode case with interactions. You see that at a large volume here, the W is less than -1, but increases approaches to -1 asymptotically. And to account the big rip singularity, we need to we can consider to introduce the total energy density of the universe. Suppose it satisfies the conservation equation, and with the equinal state equals to the effective one we gave, we see that it's approaches to a constant at a large volume, and not diverges. So it would lead to the theta space-time asymptotically. I want to emphasize that this is not trivial, because we can also consider a counterexample with W has this form, and this will lead to a divergent energy density at a large volume. So finally, we can consider more than one interacting terms in our model, and then try to combine infinitary and phantom-like acceleration at the same time. We see that at the middle range, the W is less than minus 1/3, and which correspond to and can be long-lasting, correspond to infinitary phase. And after that, the W will increase and reach positive value, indicates the end of the inflation. And after that, it decreases again, lead to a little time acceleration we observed now. So it's a brief summary. We see that the GFT group field theory can be used to extract the cosmology information, and already at the free level, we can avoid the Big Bang and have an accelerating expansion, and further including interactions will introduce will lead to little time acceleration and the possibility to combine infinitary phase and the phantom-like phase. And that's all. Thank you for your attention.